Rural Pennsylvania, 1903. A farmhouse in Lancaster County heated itself through winters that dropped to minus 15 degrees Fahrenheit, using a wood-fired boiler in the basement and a loop of iron pipe. Hot water rose from the boiler by convection. Cool water descended. No pump, no motor, no electricity, and at a time when most of rural America had none. That system heated millions of American homes from the 1880s through the 1940s. One installation, no heating bill, no replacement cycle. The electric pump industry killed it after World War II. International Residential Code Section M2101 made sure it never came back. By the end of this video, you will discover exactly why and how to install one yourself. Subscribe so you never miss what the heating industry hopes stays forgotten. Every civilization that confronted extreme cold without mechanical assistance independently proved the same physical truth. Heat moves through a medium by convection without any mechanical help. Confine that movement in correctly oriented channels and pipes, and you have a heating system that runs without electricity, without a pump, and without a service contract across any climate on any continent in any century. On the Korean peninsula, architects documented as early as 1000 BCE what they called ondol, sealed stone channels carved beneath the floor surface, conducting heat from a fire chamber through the horizontal mass of the floor and radiating warmth upward into the living space. Hot combustion gases entered the channel at the fire end, moved by convection through the channel network, and exited through a separate flue at the far end. The National Museum of Korea's archaeological documentation confirms ondol systems in continuous residential use across sites at Osuni and Seopohang for over 3,000 years. UNESCO added Korean ondol culture to its intangible cultural heritage representative list in 2018. The same year, South Korean researchers confirmed that over 90% of Korean homes still use a descendant of the same convective floor heating principle today. 3,000 years of continuous operation, no circulator pump in any of them. In Han Dynasty China, ruling from 206 BCE to 220 CE, a different solution emerged from the same physics. The kang, a hollow clay sleeping platform positioned adjacent to the cooking fire, connected by a sealed clay channel that carried combustion gases from the fire through the hollow interior of the platform before exiting through a separate flue. Research published in Energy and Buildings in 2014 documented traditional kang installations in Heilongjiang province, maintaining sleeping surface temperatures of 35 to 40 degrees Celsius during winters, when exterior temperatures dropped to minus 30. The kang transferred heat to its surface through the natural convective movement of hot gases through a correctly configured channel. Approximately 178 million people in northern China still sleep on kang-heated platforms today. Still no pump. In France in 1777, a mechanical engineer named Jean-Simon Bonhomme translated the same convective principle into water. By 1880, gravity-fed hot water central heating was standard practice in American cities. The American Society of Heating and Ventilating Engineers, the direct predecessor of today's ASHRAE, published prescriptive design standards for gravity hot water heating systems in their 1908 official handbook. Burnham Hydronics, Weil-McLean, and Peerless Boiler manufactured boilers designed specifically for passive thermosiphon loops. No pump required, no electricity consumed for circulation, different millennia, different materials, different continents, identical physics. Modern building science calls this the thermosiphon, passive circulation of fluid through a closed loop driven entirely by temperature-induced density differential. The physics are exact. Water at 72 degrees Celsius has a density of 0.958 grams per cubic centimeter. Water at 20 degrees Celsius has a density of 0.998 grams per cubic centimeter. That difference, 0.040 grams per cubic centimeter, generates a pressure differential across the vertical height of the loop. Hot water is lighter. It rises from the boiler through the supply pipe. Cool water is heavier. It descends through the return pipe back to the boiler. The circuit runs continuously as long as the boiler produces heat. Nothing moves except the water itself. A correctly designed thermosiphon loop with 24 inches of vertical height differential between boiler outlet and lowest radiator and 1.5-inch copper supply and return mains circulates at 0.8 to 1.5 gallons per minute at a 20-degree Fahrenheit temperature differential. Research published in Applied Thermal Engineering in 2019 confirmed that thermosiphon hydronic loops achieve thermal delivery efficiency comparable to forced circulation systems when pipe sizing and vertical differential are correctly specified. The penalty for using gravity instead of a pump is zero, provided the system is designed for the physics that drive it. The Energy Saving Trust, the United Kingdom's government-sponsored energy efficiency body, has documented gravity hot water heating systems installed in Edwardian-era homes built between 1901 and 1910 that are still providing effective central heating with no pump replacement after more than a century of continuous operation. The circulator pump that drives a standard forced circulation system today consumes between 80 and 200 watts of continuous electricity during heating season. A thermosiphon loop consumes zero. Over 30 years, that difference represents $3,500 to $8,750 in electricity costs at current U.S. residential rates, paid for a component that also requires replacement every 10 to 15 years. Germany's DIN 4751 standard for hot water heating installations includes prescriptive design provisions for gravity thermosiphon loops. Austria's UNORM H5110 does the same. Both countries evaluated the same physics the American Society of Heating and Ventilating Engineers published in 1908 and chose to keep a code table for the gravity system alongside the forced circulation alternative. So why does IRC section M2101 contain no equivalent table? The answer has nothing to do with physics. It has everything to do with what the gravity loop replaces. The global hydronic heating market, all hot water-based space heating equipment, was valued at $39.2 billion in 2024. Grundfos, the world's largest circulator pump manufacturer, reported revenues of approximately $4.8 billion in 2023. Xylem Incorporated, parent company of Bell & Gossett, the circulator pump brand installed in the majority of American residential hydronic heating systems, reported revenues of $8.0 billion in 2024. Wilo SE, the third major circulator pump manufacturer, reported revenues of $2.8 billion in the same year. These three companies sell one product category with one defining characteristic: it fails. The average residential circulator pump requires replacement between 10 and 15 years of continuous operation. That replacement generates a new sale, a new installation call, and a new labor invoice. A thermosiphon loop has no circulator pump. It has no component that degrades on a predictable replacement schedule. The transition away from gravity hot water heating was not market-driven. It was equipment-driven. After World War II, wartime manufacturing at companies including Bell & Gossett had scaled pump production to a cost point that made forced circulation systems economically competitive for the first time. Heating equipment distributors promoted forced circulation because it required more components: pump, expansion tank, zone valves, electronic controls, balancing valves, than a gravity loop. A gravity loop installation for a 2,000 square foot home requires a boiler, 100 to 150 feet of 1.5-inch copper pipe, and cast iron radiators. Total material cost of $500 to $3,500. A forced circulation system for the same home requires an additional pump, expansion vessel, zone valves on each circuit, a wiring center, and electronic thermostats per zone. Total material cost $4,500 to $9,000. The same heat delivered to the same rooms. 3 times the equipment sold. The Radiant Professionals Alliance, formerly the Radiant Panel Association, is the trade organization that writes training curriculum and installer certification standards for hydronic heating in the United States. Its member companies include circulator pump manufacturers and hydronic control systems companies. Its certification program covers forced circulation system design, pump selection, zone valve sizing, and electronic control configuration. It contains no training module for passive thermosiphon loop design, the system that requires no pump, no zone valve, and no control system. International Residential Code Section M2101 governs hydronic heating installation in American residential construction. Its pipe sizing tables, pressure testing requirements, and flow velocity guidelines are written entirely for forced circulation pump-driven systems. No table in Section M2101 addresses the minimum pipe diameter, minimum vertical differential, or maximum horizontal run length required for passive thermosiphon circulation. A building inspector encountering a correctly designed gravity loop has no code table to reference. The default answer is no. But you do not need anyone's permission to understand the physics. Here is exactly how to install one yourself. Before you purchase a single length of pipe, 3 pieces of information govern every design decision that follows. First, your building's vertical geometry. A thermosiphon loop requires the heat source at the lowest point of the system and every radiator positioned above it. The minimum vertical distance from the top of the boiler to the bottom of the lowest radiator is 18 inches. Less than this, and the pressure differential driving circulation is insufficient for cold morning startup conditions, when the temperature differential between supply and return is at its smallest. If your home is a single-story building on a slab foundation with no basement, measure before you plan. The vertical differential requirement is not flexible. Second, your local building department's position on alternative heating methods under IRC Section R10411. Contact your building official directly and ask whether passive thermosiphon hydronic heating has been reviewed previously in your jurisdiction. Budget for a mechanical engineer's stamp on your drawings. $500 to $500 from the beginning, not as an afterthought when the permit is denied. Third, a manual J heat loss calculation for your home, available from any licensed mechanical engineer or HVAC designer for $150 to $300. This number determines your boiler output requirement and your radiator sizing for every room. Do not estimate it. Use type L copper pipe throughout. The supply and return mains require a minimum 1.5-inch inside diameter. Do not substitute 1-inch or 3/4-inch pipe. Those dimensions are sized for forced circulation systems where a pump provides the driving pressure. In a gravity loop, pipe diameter is the primary determinant of flow rate. Undersizing by a single nominal dimension reduces flow by more than 50% and reduces the system to an expensive space heater for the boiler room. Use lead-free brass fittings at every connection. Solder every joint. Do not use press-fit fittings anywhere in the heating circuit. Thermal cycling produces expansion and contraction stresses that cold water-rated press-fit connections are not engineered to absorb across decades of operation. Install the boiler in the lowest mechanical space available. Every inch of supply pipe must slope continuously upward from the boiler outlet to each radiator. Every inch of return pipe must slope continuously downward from each radiator back to the boiler. The minimum slope is 1 inch of rise or fall per 10 feet of horizontal run. Maintain this slope on every pipe section in the system. Install cast iron column radiators, available from architectural salvage suppliers for $50 to $200 per section, or new production from Burnham Hydronics, sized to the heat loss in each room. Install an open-vented expansion system, a small feed and expansion tank positioned at the highest accessible point of the building, typically the attic. Connected to the highest point of the heating circuit by a 1-tier 2-inch open vent pipe and a 3-4-inch cold feed pipe. This is the traditional configuration used in British gravity systems in continuous operation since the Edwardian era. It provides automatic air release and protects against pressure buildup simultaneously. It is the simplest and most failure-resistant expansion arrangement a gravity loop can use. This is non-negotiable. No horizontal pipe run at or below boiler level anywhere in the circuit. A horizontal section at boiler level creates an airlock that blocks gravity circulation permanently and cannot be cleared by bleeding radiators. It requires replumbing. Run a string line from the boiler outlet and verify every supply pipe rises continuously from that point before you solder a single joint. Verify it again before you close any wall or ceiling. For homeowners in single-story slab buildings where the vertical differential cannot be achieved, a solar thermal drainback system using the same thermosiphon principle with a single 15-watt photovoltaic-powered pump delivers the same zero-fuel heating benefit, using $25 to $40 of annual electricity for circulation. It delivers 90% of the thermal performance of a full gravity loop without the basement requirement. Build this correctly and your home will heat itself for 50 years, with no pump to burn out, no zone valve to fail, and no electrician required at 2 in the morning in February. When Winter Storm Uri hit Texas in February 2021 and cut grid power to 4.5 million households, forced circulation heating systems shut down within minutes. The circulator pump stopped, the zone valves lost power, the electronic controls went dark, homes dropped to freezing in hours and stayed there until the utility restored power days later. A thermosiphon loop on the same street would have continued running as long as the boiler had fuel. No electricity required, no control board to lose power, no pump to stop. The physics of hot water rising are not grid dependent. Forced circulation heating requires working electricity, a functioning pump, live zone valves, and a service technician available during the 1 week per year, when every heating system in a cold city fails simultaneously. The thermosiphon loop requires none of those things. Jean-Simon Bonnemin proved that in Paris in 1777. Korean builders proved the convective principle 3,000 years before that, in stone channels beneath their floors. The American Society of Heating and Ventilating Engineers published the design standards for this system in 1908, and millions of American homes ran it for 60 years. Before the pump industry removed it from the code books. The density differential between hot and cool water is the same today, as it was in that Lancaster County farmhouse in 1903. The physics still work, the loop is waiting. Now you know not just why this was hidden from you, but exactly how to install one yourself. Subscribe to if you enjoyed this guide and watch the next video appearing on your screen right now.